Log on, tune in, find out. Another good idea from Cambridge.
Thank you. Okay, thank you very much. I would like to thank the organizers for giving me the opportunity to come here today, and also the audience, the last ones standing today after a long day. This is a joint work with Victor Galaktionov of the University of Bath, in which we obtain some qualitative information about the solutions of a degenerate four-order equation, of four-order evolution equation of parabolic type of the following form. In the n-dimensional case, and supposing that the parameter n is very close to 0. This equation is written for solutions of changing sign that can occur in the Cauchy problem and also in some free boundary problems. Free boundary problems with these following boundary conditions at the singularity surface, which is the lateral boundary of the compass support, the support of the solution U. And the problem is completed with bounded, smooth, integrable, compactly supported initial data. There are hundreds of papers focusing on the analysis of non-negative solutions with compass support for free boundary problems, and a lot is known about it, at least in one dimension. And in particular, I would like to mention the pioneering work of Bernice-Friedman in 1990, where the existence of weak solutions was proved, as well as the positivity of the solution when the initial data is non-negative. Moreover, in the last 2 decades, many improvements have been achieved following that direction, with applications to thin film, lubrication theory, and several other hydrodynamic type problems. For example, some non-uniqueness results of the existence of weak solutions depending on the parameter n and the initial data by Bertozzi and Pak. Some approximation when n approaches goes to 0 by Bernice, Hussolf and Quiros. A variational approximation in the particular case n equals 1 by Giacomelli and Otto. Some decay results using entropy methods, also in the particular case n equals 1 by Carrilla and Toscani, and others results supposing different boundary conditions. However, solutions of changing sign have recently gained some interest, even when there are not so many works as for non-negative solutions. Probably because these oscillatory solutions are very difficult to analyze rigorously by classical methods, definitely because of the physical applications of the others. I would like to point out that very recently, John King of the University of Nottingham has discovered some biological applications for these oscillatory solutions. Particularly interesting for us, and in connection with those oscillatory solutions, is the Cauchy problem, for which very little is known, and even principal questions as the concept of proper solution is still unknown. However, it turns out that in order to understand better such oscillatory properties for the solutions of the Cauchy problem, it's quite fruitful to consider the homotopic limit when the parameter n goes to 0 for this thin film equation. Let's say that such oscillatory solutions can be attributed to the Cauchy problem rather than to a free boundary problem posed in a bounded domain with moving free boundaries, as the one considered by Bernice and Friedman. And one of the main reasons is because the limiting problem, the biharmonic equation, and also its rescaled versions, has oscillatory solutions. Therefore, we propose to carry out a homotopic transformation, a continuous deformation from the thin film equation to the biharmonic equation that we know has oscillatory solutions, visualizing somehow such an oscillation on the solutions of the thin film equation. obtaining in addition some qualitative information and certain multiplicity results when the parameter, when n is close to 0. This follows a similar idea carried out in the 70s and 80s for the degenerate second order equation, the so-called porous medium equation, with added difficulties such as the lack of maximum principle, comparison methods, potential theory, and so on, that are not available for our four-order equation. However, even for this second-order case, there are a lot of open problems when the solution, when one considers solutions of change sign. To do so, to obtain our results, we will use the real scale equations for the thin fin and for the limit case, the biharmonic equation. And we'll use the classical branching theory by the Lyapunov-Smith reduction, using the patterns happening for n equals 0 as branching points of our solutions, of the solutions of the thin film equation. So now I'm going to introduce you all the different real scale equations I have, we have been working with. For the thin film equation, as you could see on the title, we have worked with global in time solutions and blow up in finite time solutions. So by scaling invariance of the problem, the global solutions for the thin film equation have this self-similar structure, with alpha and beta related by this way, and assuming conservation of mass in a case of non-zero mass, and with F solving this nonlinear eigenvalue problem. This is the real scale equation. In a similar way, we obtain these blow-up self-similar solutions with F solving, in this case, this nonlinear eigenvalue problem. Obviously, for the blow-up case, we don't have solutions with compass support as in the global case. So, but we impose a condition of minimal growth that give us the right boundary conditions at infinity. And for the limiting case, for the equation, for the case n equals 0, the biharmonic equation, the following is known. The Cauchy problem for that biharmonic equation has a unique solution given by this convolution Poisson type integral, where u dot is the initial data and bt is the fundamental solution of the parabolic problem. With this self-similar structure, and with F solving this linear elliptic problem. This will be our real scale limit equation. Observe that the operator, the linear operator B, is a non-symmetric operator and is defined between these two exponential weighted spaces, thanks to or by the fact of the exponential decay of the real scale fundamental kernel at infinity. And also, I need to impose, or we will use some spectral properties for these linear operators in order to obtain our results. So the main result in the paper of Egorov, Galakhtianov, Kondratyev, and Posaev established, or the most important for us at least, established that the spectral properties for the linear problem of the operator B are as follows. The spectrum of this linear operator, this limiting linear operator, has an infinite number of eigenvalues with finite multiplicity, and the subset of eigenfunctions is complete, so eigenfunctions under this expression, and also the resolvent is a compact operator. They also establish that for the adjoint operator, the spectrum is the same, and the eigenfunctions have this polynomial expression for the beta. These are some type of Hermite polynomial functions, or generalized Hermite functions. Then, keeping all of these real scale equations and spectral properties for the linear problem and so on in mind, we perform a homotopic deformation, a continuous deformation from the thin film equation, in this case for the global case. I will give you some details for the global case, to the corresponding of the biharmonic equation when the parameter n goes to 0, obtaining the following: a countable family of solutions that consider as nonlinear eigenfunctions associated with certain values of the parameter alpha that we call nonlinear eigenvalues. Now, how to prove this? Because it's the last talk of the day, I will try to keep it as simple as possible and as clear as possible. I try not to put many details. So, due to the conservation of mass and the scaling we have used, we have these expressions for the parameters alpha and beta. So it turns out that when n goes to 0, we obtain certain critical values, certain for that parameter alpha that we call nonlinear eigenvalues. Those critical values, in this case just for the first one, have this expression. So it looks like the solutions for the thin film equation approach the eigenfunctions of the linear problem. In this case, the first eigenfunction, c dot, associated with this first eigenvalue, lambda dot, in this case equals 0. And this can be extended for the rest of the eigenfunctions. So we have our family of nonlinear eigenvalues. Because of the relation with the linear problem, that branching set will depend on the spectral properties of the linear part, and I will show you that. Indeed, it looks like the discreteness of the spectrum for this operator B, it will be inherited by our thin film, the solutions of our thin film equations. In fact, the solutions, the nonlinear eigenfunctions and the nonlinear eigenvalues we will obtain in the end. So once we have obtained that expression for our parameters, those critical values, we can use these expansions and observe that the second one can only be supposed if the zero surface of the oscillatory solutions is transversal. Otherwise, it's not true. So we need to impose it. And I will give you a few details about that at the end of the talk. So substituting those expansions into our real scale equation, we obtain this nasty and ugly equation. Now, under that transversality condition and using those expansions, we have this, we can use the Lyapunov-Smith reduction in order to obtain the branching equation of the branching equation. So f, the solutions, can be splitted by the corresponding eigenfunction for the appropriate kernel plus a function belonging to the complementary invariant space. At this point, and because of the spectral properties I explained before, we distinguish two different cases. One of them is when the eigenvalues is simple. So we define the projections P0 and P1 onto the corresponding kernel and the complementary invariant space, such that f is splitted by the c dot, which is the generator of the kernel, plus that function v dot that is represented in this way. Then, substituting them into that equation I showed you before, this one, substituting f here and passing n to the limit to 0, we obtain this inhomogeneous equation for phi 1, 0. Now, if I apply the Fredholm alternative, the v dot exists if and only if the right-hand side of the equation is orthogonal to the kernel of the adjoint operator. So, doing that, multiplying by the adjoint engine function, I obtain just one solution for the expansion of my parameter. So there will be just one branch of solutions this is n. I have just one branch of solutions emanating at n equals 0. On the other hand, when the engine values are semi-simple, doing the same splitting for the function n, and under this normalizing constraint, I have this non-linear algebraic system that when the dimension of this kernel is 2, I obtain two branches of solution emanating at n equals 0. And when the dimension is 3, I have at most 4 branches of solution that emanating there. We believe that 2 of them coincide, but we don't have a rigorous justification for that fact. So, similarly, for the blowout case, one just has to obtain the right critical values for the parameter alpha, depending on the operator B star, and using the spectral properties for this operator B star, obtaining the similar conclusions. Obviously, in this process, many difficulties arose. Observe that for the global case, those functions with compass support can be replaced by others, maybe more appropriate, deduced in the case n equals 0 to justify the exponential decay of the kernel at the engine functions at infinity. Again, there is no rigorous justification for that, and actually it's not clear how to do it. But let's say that the boundary conditions stated for this problem are related with the finite propagation of the solutions for thin film equations. So any assumption of stating that f is sufficiently small at infinity will lead us to compactly supported solutions. Also, for the transversality of the zeros, this is something that we need to impose because we don't know how to prove it. There are some numerical, and it's non-qualitatively, actually there are some numerical analyses in one dimension at least, proving that those zeros are transversal, but it's not clear how to prove that. So any situation like this, for example, or something like this, is not considered here. And for the minimal growth condition, we need to impose this in order to make our problem a non-linear eigenvalue problem. So we have two types of asymptotics at infinity for this thin film equation. One of them is non-linear, and the other one is linear. And actually, the linear one is the minimal growth condition we need to impose. However, we cannot justify rigorously again this minimal growth in order to have our problem well posed and with a countable family of solutions. And finally, for non-small n's, a different approach must be used. And very recently, I have proved that there is not a bifurcation from the branch of trivial solutions. And because there is not a oscillatory solution when n is bigger than 1.758, something like that, whatever. There are only oscillatory solutions when n is smaller than that value. So the existence of oscillatory solutions is not guaranteed for any n. It's more than likely that there are some turning points, infinitely many turning points, and probably the solution goes forward and backward, joining again one of those branches and going back again and doing some kind of loops. And with this, it's all. Thank you very much.
Thank you very much. Any questions? Comments? So maybe you had a sort of a general statement, the main statement that there was a countable number of solutions.
Yes.
Could you repeat the conditions of solutions, regularity, decay? You had just the general statement there.
You can repeat them, but the problem is any try to talk about regularity is a very slippery surface. So it's very difficult to justify any regularity for the solutions, because the problem with this equation is that the generation is so strong that it moves everything very quickly. So one must be careful to justify those regularities. That's why I say that we impose that the solutions are compactly supported, but maybe that's not the right way to do it. We don't know, because it looks like if we pass to the limit to the real scale by harmonic equation, the regularity is completely different. I don't know.
Okay, then we thank Pablo.